So I'm trying to record today because I forgot to record 9:30, so I'm going to record this class. So I'm going to do a lot here instead of the board, just so it's captured. But what we're talking about in the chapter is the central limit theorem. It is the kind of like the foundational theorem of all statistical inference. And I'd like you guys to tell me the three main things that we learned both from the slides, the theory, and the practice when we rolled those die. We rolled 1, we rolled 2, we rolled 3, we rolled 25. What do we learn? What is the central, there's three things, three components that the central limit theorem tells me. Go ahead, Katie.
With rolling the dice, like, it should be equal every time.
Okay, so, one thing we learned is that the mean of the sampling distribution is equal to the original mean. If you remember that die, we rolled 1, it averaged a 3.5, right? We rolled 2 and averaged them together, 3.5. We rolled 9, 3.5. 25, 3.5. So the mean did not change. That's one thing we realized is the mean did not change. That was number one. There was two other things. What else did the central limit theorem tell me? What are the two other things? Brianna? Okay, so what we also learned is that if the original shape was not normal, when I say normal, I mean like bell-shaped, if we sampled enough, it became normal. And if the original shape was normal, it stayed normal. Remember when we looked at the die, it was like kind of uniform. Everything had equal opportunity or equal likelihood. But if we sampled 2 and then 6 and then 25, it became normally shaped. So that was good. And what's good to know for us is we know everything there is to know about this curve. So hey, if it becomes normal shape, that's all good for us. What was the second thing then? The second thing that I'm missing here. So the mean stayed the same. It became normally shaped. But what else did we learn there was a relationship? Remember, what was the difference between 2 die and 3 die, and then we went up to 25 die? What changed? Very good. Malik says like this, right? The more I sampled and averaged together, the tighter it got. And basically, we learned that the variance of the sampling distribution is equal to the original variance divided by n. Okay? Or the standard deviation of the sampling distribution is equal to the original standard deviation divided by the square root of n, right? So that was the things that we learned. The more we sampled, the tighter it got around that mean, which did not change from the original distribution. So how does that help us? Well, we already know in the previous chapter, we had a formula that converted x, 1x, into z, the standard normal curve with a mean of 0 and a standard deviation of 1. Well, what I'd really like, and what I'm using this formula for is, or this theorem for, is to say, all right, I want a formula that converts sampling distributions into z values. So instead of converting x's to z's, I'm going to convert x bars, or sample means, to z's. What's the formula tell me? Well, the formula tells me the mean stays the same. Great, I'll just leave that alone in the formula, right? The mean's the same, so why change it? It tells me the standard deviation is equal to the original standard deviation divided by the square root of n. So that's all I'm going to do. So my new formula that I'm going to use to convert x bars to z's looks like that, right? And it's derived via the central limit theorem. Okay, it's derived via the central limit theorem. So the homework that we gave, that I assigned, all used that formula. So let's do at least one, maybe two. This is chapter 8. And I assigned you number 9, right? That was when I assigned you? Yes? Okay, so let's do number 9. it says the amount of time that university professors devote to their jobs per week is normally distributed with a mean of 52 hours and a standard deviation of 6 hours. What is the probability that a professor works for more than 60 hours per week? Find the probability that the mean amount of work per week for 3 randomly selected professors is more than 60 hours. Find the probability that if 3 professors are selected at random, they work more than 60 hours each. Okay, so let's draw our original distribution. It says university professors average 52 hours of work a week with a standard deviation of 6. It wants to know what's the odds that if we sample one professor, just one, we're talking about X, that they work more than 60 hours. Does this make sense? So we're just talking about X, not X bar. I can use this formula to convert X's to Z's, and I'm going to do that. The probability that X is greater than 60 is the same as 60 minus 52 divided by 6. Oops, that's all I need. The probability that Z is greater than 8 divided by 6. The probability that Z is greater than 1.33. So I need to look up 1.33. 1.33 gives me 0.9082. Because it's greater than 1 minus 0.9082, it says there's a roughly 9% chance that a given professor at this university works more than 60 hours a week. Is that good? Now part B is a little different. It says instead of talking about one professor, I'm going to sample 3. I'm going to average them together. So I'm no longer talking about X, I'm talking about X bar. And we're saying what's the odds that those 3 professors have an average greater than 60? So I'm sampling 3. What's the odds that the average is greater than 60? Well, let's think about it. Before we figure out the math, let's think about it. Now we're doing a sampling distribution. We're taking 3 professors and averaging them together. The mean doesn't change, right? Still stays 52. What's happening to the curve, though? The mean stays the same, but we sampled more, so it gets tighter. So I'm going to draw that. Wow. It's going to looks like it's going to be smaller, right? There's less away from the mean. 60 is away from the mean. So let's see. The probability that Z is greater than, well, now I have to change this formula to this because I'm talking about X bar. So 60 minus 52, 6 divided by the square root of 3, because 3 is n. Probability Z is greater than 8. 6 divided by the square root of 3, let's see. Uh, 6 divided by 3 square root. I think that gives me 3.46 down here. 8 divided by 3.46. Gives me the probability that Z is greater than 2.31. Now let's look up 2.31. I get 0.9896. 1 minus 0.9896 gives me 0.0104. Okay. So it goes down. Okay, it goes down. How about this? And this isn't a problem it gave me, right? But let's say I sampled 36 of these professors. Instead of talking about 3, I went big and I sampled 36. What's the odds that those 36 professors are going to have a mean greater than 60? What happens if I sample more? What's going to happen to that curve? It's going to get even tighter, right? Mathematically, tighter. Let's convert that to a Z value. 60 minus 52. 6 divided by the square root of 36. That's 8. Square root of 36 is 6. 6 divided by 6 is 1. Probability Z is greater than 8. What's the probability Z is greater than 8? Virtually 0, right? So what it's telling me, think about it, what it's telling me is that shouldn't happen, right? So if I do go out and sample 36 professors, calculate out their mean, it comes out to be, I don't know, 61 hours. What does that make me think? A couple things. What could it be? What could explain that? It shouldn't happen. Virtually impossible, virtually zero, and it just did, so what does that make me think? Come on. That's the number, but what's the meaning behind the number? That's the more important thing. What's the meaning behind the number? Mr. Meyer? Yeah, we're saying it shouldn't happen, so maybe our original claim of 52 hours, I mean, it shouldn't happen. If it's 52 standard deviation 6, I shouldn't sample 36 and get a number that big. And it just did. So maybe I'm underreporting the number of hours these professors are working. Or the other thing is maybe my sample was wrong. Maybe I happened to sample, I don't know, it wasn't random and I sampled the hardest working department, right? Business, that would be business. Or something to that effect. Does this make sense? So C, we didn't do C, but let's do C. C says, hey, what's the probability that I select 3 professors at random and they all work more than 60? Not that I average them together and that average is greater than 60, but each one of them works more than 60 hours. What's the odds that I pick one and she or he works more than 60 hours? We figured that out in part A. What's the odds that I pick one and he or she works more than 60 hours? Roughly. 9%. So what's the odds that I pick 3 and each work more than 60 hours? How would I figure that out?
Elevation.
What's that?
The elevation.
The elevation?
Yeah, I mean, like 0.918
Right?
at third.
To the third power, right. Yes, to the third power. Because think about it. If I were figuring out what's the odds that I get 3 tails in a row when I flip a coin? Remember the probability tree? 50% times 50% times 50%. Remember that path of 3 tails? What's the odds that I get 3 professors randomly that work more than 60 hours? He's right. 9% times 9% times 9%, which gives us 9% to the third power, which is, it's actually 0.0918 to the third power, which is a very small number, right? 0.00007. Okay. Does that make sense? Now, where do we use this? Well, where we use this, I like number 11 in the book. Okay. And I'm going to do that one a lot faster, but I like number 11 in the book because this is an example of this. So you never know where your life's going to end up, right? Like I didn't think I was going to be a professor, and now here I am, right? You know, there's people that do things that they didn't even know existed, and that's their life's mission, right? So you may be like a quality control manager for a salmon company. I don't know. That could happen. It's not impossible. There are people that do that. There are people who say, I am the quality control manager for, what's the tuna brand? I can't even think of it. Yeah. StarKist. Isn't it StarKist? Yeah. So you may have a promising career in quality control at StarKist, right? And they're saying at StarKist, they're saying that if our machinery is operating properly, we say they're 6 ounces, but the machine's not perfect, and it's producing cans of salmon with a standard deviation, a mean of 6.05 and a standard deviation of 0.18 ounces. That's what they're saying, right? So I'm in charge of quality control, and I got to make sure that people aren't getting gypped, or we're not giving up too much salmon or tuna or whatever the hell we're putting in these cans, right? I got to make sure, but I cannot measure every can. I cannot sample every can. So quality control, auditing, is about taking samples. So apparently, we sampled 36 cans here, and we got a sample mean less than 5.97. Okay, less than 5.97 when we sampled 36 cans. I want to know what the likelihood is of that happening. So I'm going to say, well, let's convert that to a z-value. 5.97 minus my mean of 6.05 divided by my standard deviation divided by the square root of n. In this case, I sampled 36. Well, that comes out to be the probability z is less than negative 0.08. 6, that's 0.03. The probability that z is less than negative 2.67. Okay. Mathematically, 2.67 tells me 0.0038. The odds of this occurring is 0.0038. So you have achieved your lifelong ambition of quality control manager for StarKist Tuna. You take this sample and it comes out to be less than 5.97. What is your response to your boss, or what do you do next? You say, oh, you figure out that number, but what do you do next? What conclusion do you reach? I made terrible mistakes because I'm the quality manager for a tuna company. No. What conclusion do you reach? Sydney? What do? That's the number, circle it, but that's only half of what we're doing here. The number is important, but what? What does it mean? What do you think? No? Jenna, what does it mean?
He's doing a good job making sure the right amount.
You're saying
No,
things are working well?
sure.
Okay. So what we're saying, think about this. They're saying if these machines are working properly, the average in them is 6.05, and the standard deviation is 0.18. Okay? That's what we think the machine is if it's working right, that's how it's calibrated. It says if we randomly sample, if that's the case, and we randomly sample 36 cans and take an average of the amount of tuna in those cans, and it comes out to be less than 5.97, the odds of that occurring is very low, 0.0038. But I just took a sample and it happened. What does that mean? Very unlikely to happen, but it happened. What does that mean? What does that mean? So I tell you that the average St. Francis University graduate, and I think I use this, makes $100,000 a year first year out of college. And you say, that's BS, Dr. Miko, right? So you say, you do a sample, and you sample 10 people you knew graduated from the School of Business last year, 15, 20, I don't care. And you take an average and it comes out to be 40,000 or 50,000 or 60,000. And you're saying statistically that should not happen, and it just did. So what does that make you think, Connor? Sure. I would say if I worked for this company and I was the quality control manager, I'd say, you know what, this machine is not calibrated correctly. It is producing, we're shorting, it's too low, right? We're saying it's too low, and I'm almost damn near positive, 99.62% chance that this machine is off. There's only a 0.0038 that it's actually working properly. So I'm going to go in and have my machinist or whoever the hell does that adjust the machine, right? And then I'm going to resample and say, is it fixed? Does this make sense? Some of you guys are accounting. You'll be auditors. You'll audit places. You can't go in and look at every financial transaction. You can't. So what do? You take a sample and you look at sample statistics, and if those things look odd or not like the claim, then you say, hey, there's inference that what you're saying isn't real life. You know what I'm saying? That's what a sample is all about. So this is kind of backwards thinking. We're starting out with a claim and then seeing if there's evidence that we can refute that claim. But this is what I would say here, right? Connor, right? If Dr. Fry says $100,000 the average starting salary, you're like, but I don't want to call Dr. Fry a liar. But then when you have math that says, hey, that shouldn't happen, and it just happened, either I just sampled the worst graduates randomly, or that claim is incorrect. Does this make sense? You guys know what I'm saying here? Okay. And this is kind of like backwards thinking. When we get to the next chapter, estimation, it's more forward thinking. We're saying, we don't know what the population parameter is. Let's try to go investigate it. It's more forward thinking. But before we do that, I want us to go back in our statistical time machine. And I want you guys to remember we talked about 3 types of data in chapter 2. Way back in chapter 2, we talked about 3 types of data. What were those types of data? Give me one type of data. Marcus? Very good. So nominal was like categorical data, like gender, all those good things, religious status, major, marital status, party you're affiliated with, hair color, nominal. What else? Very good. Someone said interval, and someone said ordinal. Very good. So ordinal was kind of categorical ranked. Interval was real numbers. And what was nice about interval, real numbers, I could calculate out things like mean, right? So sample mean I can do, population mean I can do, right? I can add them up, divide by how many there are. That's what we were just doing. When I have nominal ordinal data, how do I describe that? I can't do a mean. How do I describe that? What is the measure I use to describe that? Desiree, if I asked you to describe the gender makeup of this class, how would you do that for me? Like the gender balance of this class. You don't have to be right, just if you had to give me an estimate, how would you do that? The gender balance of this class. People in our room. What's that? Male, female, right. And I want you to give me something that's descriptive about it. So you just eyeball it. What would you say? How would you assess the makeup here? Is it all males, all females, or a mix? It's a mix, right? So give me a number that describes that mix. So let's say we have 10 females out of 30. What would that mean? Come on. How do you describe it? Come on.
What kind of data is it?
Yeah, we know it's nominal data, gender, right? Who's talking? Oh, Katie. Sorry. 10 out of 30 would be what? 33%, right? That's a way we can measure, right? That's how you describe, like, hey, 90% of the time, 90% of the people in this class are Republican, right? That's 33% are female. So what do we call that, like a percentage? What do we call that in the world of statistics? What's not a percentage, what do we call that? I guess, yeah. A proportion, right? A proportion, right? A proportion, like a ratio, a proportion. 33% female, 67% male. That's a proportion. So when we have nominal and ordinal, nominal, I just made up a new term, nominal. Nominal or ordinal data, we can't do means, right? We can't average it. We're talking about proportions. And the two terms we use, we're talking about population proportions. We're going to use P. We're talking about sample proportions. We're going to talk about P hat. So we're still talking about a sampling distribution here, but we're no longer talking about something we can do a mean with. We're talking about something we can do a proportion with. So I need to work with a proportion. Well, I'm going to give you a formula, just like we had a formula that converts X bars to Z values. I'm going to give you a formula that converts sample proportions to P values, to Z values, I'm sorry. And that's this is the formula we're going to use for this next section. All right, so I'm going to rip like an example from the headline. What's going on big this week, specifically on Friday? Yeah, so the inauguration is happening on Friday. A lot of news around that right now. I don't want to get political by any means because that just causes bad feelings. But I saw a statistic this morning, okay, about President-elect Trump's approval rating. I don't know, did anyone see that article? Marcus? Go ahead, Marcus. Go ahead.
Didn't we have like a 40% approval?
Okay, very good. So they do an approval rating of the incoming president the week of the inauguration. His currently is 40%. Okay, that's his approval rating right now. Did you read the whole article, Marcus?
Wasn't like disapproval at 70?
I guess it was, I don't know, I can't remember. But they look at historically speaking. Did you read like they looked at Obama, George W, George H.W, Clinton, and you remember what their numbers were? Yeah, they were like 80%, 70%, 80%, right? Okay. So, yeah, whatever. So it is what it is. So let's say I work for the Trump campaign, Trump transition team. He'd probably fire me pretty quickly, but let's say I did. And I came up with, before this information that Marcus and I saw this morning came out, he made a claim, or we put in a press statement that, our approval rating, is off the charts, and it's the highest it's ever been for an incoming president, and we're saying it's 85%. That's what I'm claiming. I'm part of the Trump's campaign transition team. I'm claiming my approval rating is highest it's ever been for an incoming president, 85%. Okay? So when we're talking about a population proportion, we're talking about P. I'm claiming that it's 85%, 0.85. Marcus, based on what you read this morning, what do you think about my claim? Is it accurate? You think? You trust me? Great. Great. I like people who just trust me blindly. I know you trust me. You should. Do you trust that? So came out today and say 85%. Do you trust that? You don't think that's true? So okay. So it's your word against me, and I'm part of the, I'm an important person. So how do you come up with evidence to dismiss that claim? You don't know? What would you do, Connor? Okay. So how many would you sample, Connor? You'd do it randomly, right? How many would you sample? A good 200, right? Okay, I like that, all right. So you sample a good 200. We'll do n is equal to 200. And let's say in that sample, it comes out to be, I saw 40% this morning. I think I saw 44% the day before. But let's say, what is the odds that it comes out to be less than 45%? That if I sample 200, that's what Connor wants to sample, it comes out to be less than 45%. I want to figure out the odds that it comes out to be less than 45%. Okay. Well, how do I do that? I need to convert that p hat to a z value using this formula. Let's see, the probability that z is less than 45%. We think the population parameter of the claim is 85%. So anywhere there's a p, I put in 85, 1 minus 0.85, divided by n, which is 200. You guys with me? So all I'm doing is putting this formula in to convert that p hat to a z value. You guys with me? Yes? So the probability that z, that's going to be negative 0.40. Denominator, I got some work to do. So let's see. It's going to be, I don't know if you can see my calculator, 0.85 times, well, 1 minus 0.85 is 0.15. Divided by the 200 that Connor said for me to sample. And then there's a root symbol, so I'm going to take the square root of that. And I get a denominator of 0.0252. So the probability that z is less than 0.40 divided by, or negative 0.40 divided by 0.02552, probability z is less than negative 15.7. So what is the odds? What is the odds of that occurring? Anyone? Okay. But I just did. I took a sample of 200. Me and Connor went out and sampled 200 people randomly. And we got approval rating for President-elect Trump at less than 45%. What does that mean? Because I'm a powerful dude. Now, what do you think? Huh? Lies. So we're saying that's virtually impossible. If its true population or proportion approval rating is 85%, the odds that I go out and sample 200 and get an approval rating less than 45% is virtually zero. It just happened. So either it was a bloody miracle, like I just happened to hit the the anti-Trump headquarters, but if I did a random sample, it shouldn't have been, right? Or the original claim is inflated, right? And that's the case, right? That's the case. Does that make sense? Yes? Do you guys understand this? So it's kind of reverse thinking, but same thing. All the time, people come out with something, they make a claim, and then you could say, well, how do I get evidence to dismiss that claim or support that claim? A lot of times, the answer to that is the same. I want you guys to do one. So I want you to do 23. What do you guys think of our bookstore? Yes, no, you like our bookstore? Satisfied with our bookstore? Huh? I don't hear any numbers. No. Yes, no, you satisfied? Absolutely. Eddie? Sid, you satisfied? Sure. Connor? All right, so that's pretty good. How about Luca? Our bookstore, you like that?
Yeah, I like it.
All right. Jenna? Yeah, okay. So bookstores are notoriously, campus bookstores are notoriously not liked, right? So a university bookstore claims that 50% of its customers are satisfied with the service and prices. Do you think the price of the bookstore? Okay, yeah, that's a little high, yeah, okay. So a university bookstore claims that 50% of its customers are satisfied with the service and price. That's what they say their P is, right? Their population proportion is 50%. If this claim is true, what is the probability that a random sample of 600 customers, students, I guess, less than 45% are satisfied? How would I figure that out? Okay, how would I figure that out? And I'm going to put back on the screen here, if I can find it. The formula I use. So there's the question. There's the formula you need. I like this document. You guys like that? Is that better than board? Is that better than board? Board or that? Board? Indifference? How about if I scrawled stuff in the dirt? Good? Indifference. Student apathy. Yes. Less than, so less than 45%. What is 600? And what is 50%? P. All right, so let's do this together, okay? So a university bookstore claims that 50% of its customers are satisfied with its service and prices. So that's P. That's our claim about everyone, the whole population. That's P, population proportion. If this claim is true, what is the probability that a random sample of 600, n is equal to 600, less than 45%, that's the sample proportion, are satisfied? So if we look at this, what we're saying is, hey, what's the probability that P hat is less than 45%? Well, we can convert that to a z value. P hat minus P divided by the square root of P times 1 minus Z divided by N. So the numerator is pretty easy, negative 0.05. But the denominator, I think I saw some people struggling with the denominator, so let's do it together. It'd be 0.5, whoops, times 1 minus 0.5, which is also 0.5. That gives me what did I do? 0.5 times 0.5 gives me 0.25, divided by 600, and then we take the square root of that, and it gives me 0.0204. It's my phone. Well, there's apps. This is called it's called Real Calc, I think. It's nice. Yeah, it's called Real Calc. Yeah. You guys listen to podcasts? I got into those over break. Anyone listen to podcasts? It's kind of an old man thing, I guess. Yeah, but it's pretty nice. If you, so comes out to be the probability Z is less than negative 2.45. I looked that up and it comes out to be 0.0071. So less than 1% chance of that happening. If the true satisfaction rate is 50%, the odds that I take a sample of 600 and it comes out to be less than 45% is less than 1%. Part B says, hey, I just sampled 600. 270 said, yeah, I'm happy, I'm satisfied. That's 45%. So that just happened. What does that make me think about the bookstore's claim and why? What does that make me think about the bookstore's claim and why? That it's what? Okay, it shouldn't have happened. I shouldn't have been able to sample and get less than 45%. And I did. So that makes me think there's something wrong with that original claim, right? That they're maybe bloating it a little bit, right? Here's what I want you to do, and don't pack up because we're not done here. I'm going to give you 4 of these for homework, but you can do 2. You choose 2, your choice, because I want high satisfaction out of my classes. 18, 19, 21, and 25. They're on page 132. I want you to choose 4 of 18, 19, 21, and 25. Page 132. And probably, it seems like I should homework check. All right. What's that? We're not done. So we're going to move on. And the next chapter I want to introduce, but we're not going to do any work in it today. So under chapter 1, we started talking about 2 branches of statistics. And there was descriptive versus inferential. I remember writing that on the board week 1. Can you guys see that? There we go. And under descriptive, how do we describe data? We did it with numbers, numerical, we did it with graphs, graphical, and we did it with tables, tabular. You guys remember? Good times. In inferential statistics, the two main things we're going to do are estimation and hypothesis testing. And I should add to the front of those statistical, because we do estimation and hypothesis testing all the time, but we're going to study statistical estimation and statistical hypothesis testing. So, for example, who lives off campus? Someone who lives off campus, all right? So where do you live? I'm not stalking. Where do you live, Sydney?
I live like in Loretta, but off campus.
All right, in Loretta. How long is it going to take you to walk back? 3 minutes, okay. And that's an estimate, right? She just gave me an estimate, a non-statistical estimate, but it's an estimate. And are you 100% positive that it's going to take you 3 minutes? No, why? You never timed it, you're just guessing. It might be icy, you might slide down that hill, you might run into a friend, right? Some things happen, yes? So that's an estimate. We estimate a lot of things. Where am I going to be in 5 to 10 years? What's my GPA going to be this semester? We estimate a lot of different things. Statistical estimating is a little bit different, but we're going to use a non-statistical estimation technique to introduce some terms that we're going to use in the estimation world. So I need a couple volunteers, and I would like 2 male students and 2 female students. Connor's one. And I would like one of those male students to be a football player. We have football players. Malik, okay. So Connor, Malik are my male students. Who are my female students? I'm looking at you, females. So Sydney and Jenna, okay. So here's what I want you to estimate. So Jenna, you're going to go first. So Jenna, I want you, Sydney, N, right? Yeah. CM and MD. Right? All right. So Jenna, I want you to estimate my weight. No, it is fair. You cannot hurt my feelings, Jenna.
I don't know. 150.
Okay. Sydney?
210.
Connor? 6'1"-ish.
Yeah, 215.
Oh, okay. And Malik?
240, 235.
Okay. All right. So what we gathered there, and this is a statistical term. These are one point to estimate my weight. These are called point estimates because they're 1 point to estimate something. So these are called point estimates. I want you to think about this. Weight is a continuous variable, right? So what's the odds that any of these are correct? Virtually zero, because even if I'm 210, I'm not going to be 210.0000000. I'm probably 210.00031. You know what I'm saying? So the odds that any one of those is correct is virtually zero. So those aren't very useful to me. If their odds of that they're right is virtually zero, I don't want to use something that I know isn't right. So how can I correct that? How can I get something that has a chance of being right? Because 3 minutes for you to walk, no way that's going to be 3 minutes exactly. Favorite color? No, sticking with weight. I'm not changing the game here. What do you think? If 1 point doesn't do it, what can I do? I like that. So what we use in the world of statistics, instead of point estimates, we use something called interval estimates. And it's a range. And Katie's right. the range, we call the bottom of the range the LCL and the top the UCL. And these are terms that you'll need to know eventually. This is the lower confidence limit. And what do you think the UCL is? Very good. The upper confidence limit. And we call that range from the LCL to the UCL. We call it the CI, which is called the confidence interval. So I'm going to come back around and I'm going to ask you to give me a interval estimate for my range, for my weight, Jenna. So you gave me 150 as your point estimate. Give me a interval estimate.
Like a range.
A range, yeah. Give me a high and a low.
150 to 200.
Okay, you're not giving me any on this end, huh? All right. So 150 to 200, and Sydney?
210 to 240.
Not giving me any on this end either, are you, Sydney? So 210 to 240. Connor?
210, 250.
Okay. And Malik?
220 to 235.
All right. So if I were to ask you, Jenna, these are all ranges, right? These are all confidence intervals, but one thing that goes along with a confidence interval is something called a confidence level. Okay, a confidence level is how certain I am that my true weight, whatever the hell it is I'm trying to estimate, is in that range. So Jenna, what's your confidence level that what I weigh is actually between 150 and 200? How confident are you that what I weigh is actually in that range?
60%.
60. Okay, this is called confidence level, by the way. Sydney, how confident are you that my true weight is in that range you gave me?
80%.
Okay. Connor?
95.
Wow. And Malik?
93.
All right. All right, so a couple things. We're going to talk about confidence level in the world of statistics, but in the world of statistics, the minimum confidence level we're willing to accept in the world of statistics is 90%. So 90% or higher is what we're talking about in the world of statistics. That's the minimum we're willing to accept in the world of statistics. 60% is fine for an argument in Loretto Pub and Grill or in Lewis Hall, but in statistics, if we're not 90% confident, then we don't utilize it, right? 90% or higher, and typically when we see things published, the confidence level is 95%. That's more standard, right? At least 95%. So Jenna, I'm going to come to you and say, hey, I want you to give me a range so that you're 60% confident my weight is in this range. I want you to give me a range that you're 95% confident. So almost positive that my weight is in, my true weight.
Could there be like a limit on how many different numbers are in it?
That's fine, yeah. So you're 95% confident that I'm in 150 to 250. Okay, good. So Sydney?
205 to 250.
All right. Connor?
I'm willing to shave down a little bit. 210 to 250.
You're an overly confident young man. Malik?
224, 240.
Okay. All right, so I want you to notice, I guess, except for Connors, everyone else did what? When I asked them to be more confident, what happened to their range? When I specifically like Jenna and Sydney, when I asked them to be more confident that my true weight was in there, what happened to their range, their confidence interval? Got bigger, very good. So the same is true in the world of statistics. If I need to be more confident, if the confidence level goes up, the confidence interval is going to have to go up, right? If I have no new information, right? If you came up and picked me up, you'd have more information, right? But you don't have any more information. So if you want to be more confident, you're going to have to give a wider range. Now, I'm not picking on Jenna. I know she probably thinks that. But her range in particular is not very useful. Why?
Because you would tell you not under 55.
Okay. All right, you're right. I'd be very sickly looking at 150 pounds. I'm not my ideal weight, but 150 is not my ideal weight either. You're right. But why is that not a very useful confidence interval estimate? Yes. Yeah, it's too broad. Like if I say, I estimate your grade in here is going to be anywhere from a 40% to 100%. I'm 90%, 95% certain you're in there, but is that very useful to you? No, it's not very useful. So big ranges aren't very useful, right? We know that. But we said if we want to be 95% confident, then we have to make the range bigger. But what can I do in the world of statistical testing to get more information? There's not really a way you guys can get more information. I mean, you could come up here and hug me, I guess, and that would give you a little more information. Or I can go shirtless, I guess that would help. I don't know. But what are ways we can get more information in the world of statistics? How would we get more information in the world of statistics? Okay. And I'm not, but you're right. But I'm not even talking about this, but just generally speaking in estimation, how do I know more? In statistics, how do I know more? How am I more confident? What do I do to know more samples? So if I increase the sample size, the confidence interval is going to go down. And remember, we saw that in the central limit theorem, did we not? We sampled more, what happened? Right? More we sampled those 25 died. The more you sample, the tighter your estimate can get, right? And that is the power of this thing called inferential statistics. Now my true weight, I didn't weigh myself this morning. I think the last time I weighed myself was probably like the day before we came back. I was good in the fall. I was down to like, if I'm at my healthiest, like my best, my fittest, I'm like 195. That's like ideal, my ideal weight. Like when I feel the best. I may not look the best, but I feel the best. Right before break, maybe a month before break, I was probably around, I don't know, right around 200, right? That's probably where I was, right around 200. I think now I'm probably, you guys are pretty damn good. I think I'm probably around 213 right now, something like that. So the reason I wanted 2 females and 2 males, specifically a football player, usually females, like Sydney was very good. But usually females aren't as good at estimating male weight. I don't know why. They're usually just generally not. Like 150, I haven't been 150 since. Yeah, 7th grade probably. And football players on the male side are specifically usually the best, right? Usually they're the best because, I don't know, you're just aware of, that guy's that tall and he's built like that, he's this. I don't know, that's it. I can take him. I don't know what it is, but generally football players are the best. What was Malik? Malik, you went high with me. I don't know. That's high.
That's a sweater. Is the muscle under the sweater?
Yeah, well, yeah, I know. So what we're going to do, all right, that's it. But what we're going to do on Thursday is we're going to implement this. We're going to implement statistical testing. But those are the terms you're going to need to know.